guys, this is Janetta from Artificially Intelligent AI. Today we're going to be covering another leet-code problem. It's called Convert a binary search tree to a doubly linked list. So I'm not going to read the entire description to you. You can pause it and read it, but I'll explain what's going on in this problem. So the input is going to be a binary search tree. We'll talk more about what that means. And we want to take that and convert it to a sorted, circular, doubly linked list, and it's going to be in place. So what in place means is that what you're getting back is going to alter the binary search tree. So instead of it still being the same binary search tree, it's now going to be the circular, doubly linked list. So let's see what that actually means. So to start off with what a binary search tree is. So we see here on the right, we have a binary search tree. So binary, that means two. So that means that given a node, so here we have the node 4 as our root node, it can have a left child and a right child, and that's it. So that's where the term binary comes from. And then the binary search tree is going to tell us how we're ordering the tree. So given a node, when we go to the left child must be less than the node, and the right child must be greater than the node. So we can see that holds true in this tree that we have here. So our root node is 4. When we go to the left, we're getting smaller. So 2 is smaller than 4. And when we're going to the right, we're getting bigger. 5 is bigger than 4. And all subtrees of a binary search tree should also be binary search trees. So we have this subtree down here with 2, 1, and 3, and they're also that's also a binary search tree. So when we look at the input for that, so it's input as this list we see here. So starting from the root, then going to the children. So 4, 2, 5, and then the children of 2 would be 1 and 3. And the output that we want from this, so the output is going to be a sorted, meaning starting from the smallest node of the tree. So a sorted circular meaning that it's going to loop around. So the smallest node will be connected to the largest node and vice versa. And the doubly linked means that there are going to be a two bidirectional linkage. So we see here in this tree that it's a singly linked list. So we have arrows going in one direction. It's going from the node to the child. But in a doubly linked list, we're also going to traverse in the opposite direction. So what that looks like, we're going to have our output starting here with the head going from 1, 2, and then from 2 back to 1, 3, 3 back to 2, 3 to 4, 4 back to 3, 5, and then lastly, we're going to need to remember what this first node was and what this last node is so that we can loop. So that's going to be the output. So let's look at when we're doing a Python implementation or any kind of implementation really, regardless of your language, let's look at these class structures of binary trees versus a linked list, or in this case a doubly linked list, and see that they look really similar, right? So when we're looking here at the binary tree structure, we have these 3 variables that we need to consider. So we have the value of the node. So when I write out code for a binary tree, I might take some variable and assign it to a node, and I pass in some value. So maybe, for our head node here, I have the value of 4. So I would denote it like this. And then the node has 2 variables alongside the value. So we also have the left and right, and that's denoting the left child and the right child. really similar though to a doubly linked list. So when we think about a node in a doubly linked list, so we can now say here an node, we're going to have a previous and a next. So you can see here we have, if 2 is our node, the next is going to be 3 and the previous is going to be 1. But that looks a lot like over here when we have 2 as our node and 3 is the right and 1 is the left. So it's important noticing this when we're thinking about how are we going to craft this solution, that actually these structures look really similar, and that's why we're able to do this in place, is that we're going to utilize the functionality that the binary tree has. It's actually going to build a doubly linked list, but we're going to stay in that node class that we were given as the input. So let's jump into the solution here. So when we are traversing a binary tree, there are several different ways to do it. You can do a depth first search or a breadth first search. And in this case, we are going to use depth first. And the reason why we want to do that, again, is because we are looking for this to be sorted. So we want to go from smallest to greatest. And since we have a search tree, we know that if we go all the way down the tree to the left, that's going to be our smallest node, and that's what we want to start with, and that's going to be our first node. So by doing depth first, we actually get the result that we're looking for. And specifically, there are several types of depth first searches. So when you think about a depth first search, remember that we always have a node, we have a left child and a right child. So when you're traversing, you can go left, node, right. You can go node, left, right. Or you can go left, right, node. So for this one, we're doing in order. So we're going to do that left, node, right. So we're going to go first to the left, then to the node, then to the right. And why do we want to do that? Let's think about how that actually looks in this tree. So remember, again, if I look at this subtree down here, 2, 1, 3, and remember that I want it sorted. So if I do left, node, tree, that gives me a sorted list as my output. So of all of the types of depth first searches to do, the in order search, where we're going left, node, right, is going to be the one that gives us the correct implementation. So and you can see here we already have the code written out in Python on the left, so we're going to follow through this. So a couple of key things here are going to make this implementation possible. So first of all, let's notice how we have a nested function. So we start off with the function call to tree to doubly linked list. But then right away, I'm defining a helper function, and this is going to be the recursion function that's going to be doing all of the work. The key here, though, is that, remember, because it's circular, I need to remember this first node and the last node. As I'm traversing, I'm going to be able to build these double links in between, so that's not going to be a problem at all. But I need to remember first and last, so that once I finish all of my recursion, I can then at the very end, outside of the recursive function, I can link these guys to each other. Actually means, in case you're not familiar. Let's look at a simpler implementation. So we use non-local when we have a nested function and we have a variable that we want to be available outside the nested function. So what I mean by that is, let's say that we have some function, we'll call it outer. And then we have another function, we'll call it inner. And in our outer function, we can have a variable that we define, let's call it x, and I'll set x equal to 0. If I say non-local x inside my inner function and then set x equal to 2, and then let's say I want to print the value of x inside here, but then also when I jump outside of my inner function and I print the value of x, so this is now outside of the inner function. So what do we expect to happen here? So obviously inside this function, this print call is going to print 2. But what do we think is going to happen outside of the inner function when I call x again? Well, that's where the non-local keyword comes into play. So what it's actually doing is saying that x is equal to 2 inside of the function, but it's also passing that to the outside of that nested function. So it's also going to be printing 2 here as well. So the reason why that's important for this implementation is because I'm not passing these variables first and last. Notice that I'm not passing them as parameters to this function. So the only way that I'm holding on to them and keeping them so that at the very end I'm able to have their values intact is because they're non-local. Okay, so let's jump into this. So I start off, like I said, we're initializing first and last to none, and we're right away jumping into this helper function. And the first thing you always want to do is check to make sure that your node exists, that it's not null. So we know that that's true here. We're going to start here at 4. Node is not null. So the very first thing I'm doing, remember, it's an in order depth first search. So it's in order, so I'm going left. Jumping here to 2. Again, first thing I do is go left again. So now I'm jumping here to 1. When I'm at 1, again, I'm jumping to the left, but there is nothing to the left. So I automatically land right back here at 1. So now I'm at the end of this depth of this left child recursion. So now I can start looking at what we have going on inside. So here is where I am finding out what my first variable is, but it's kind of done in a sneaky way, because notice that we're saying, have we defined last yet? If we've defined last, then that means that I'm not at my first variable. So that's a little bit confusing. Let's see what's going on here. So in this case, last, remember here, we initialized it at none. So do we have a last variable? No, we don't. So in this case, we jump straight to else. So what are we doing? We're saying that if we have not defined last yet, then we're going to initialize or reinitialize the first variable to be our current node. So right now we're going to say that first is equal to 1, which it is. That's the smallest one, so that makes sense. Then we set last equal to node. So last will no longer be null. Last is now going to be 1. And now we are done with that. So now we can, again, we're depth first search. We did left. We did the node. And now we're going to the right. But there's nothing to the right of 1. So I jump back to 2. So I go back up the tree. So I already am here. I've just checked the left. So now I go here, if last. Is there a last? Yes, there is. So I can go into this if clause. So now what are we doing here? Now this is where the linkage happens, okay? So here I'm saying last, which is 1. So the right is going to be the current node. And the current node's left is going to be last. So let's talk about what just happened there. So at this point right here, I have that my node is equal to 2, my first is equal to 1, and my last is also equal to 1. So what I'm doing is I'm saying that last, his right, is going to be the current node, which is 2, and my current node, his left, is going to be 1. So I've just made this double linkage happen. That's the key to understanding this problem. If you can understand what just happened there, then the rest is gonna fly by. Okay, let's move on then. So we just did that. So now we can jump out of this if, and we go to last equals node. So now I am moving last. So I'm updating last to now be my current, which is, let's put that in blue, which is 2. Because that's the last node that I visited before I'm doing more traversals. So now that I've updated last to 2, I am now going to go right to 3. So now I look and see, does 3 have a left? No, it does not. Is there a last? Yes, there is. So now I'm going to work on this inner stuff with 3. So I have, first I'm not using anymore, but I'm using that my last is 2 and my current node is now 3. So what does it tell me to do? It tells me last dot right is my node 3, and my node dot left is last, which is 2. So now we've got that linkage, and now I update. So now I'm updating last to be 3, and I'm moving back. First I'm checking to see if 3 has a right, but it doesn't. So I'm moving back. And now I'm done with the right side of 2. So now 2, he's done with all of his children. So now we jump back up to 4. But let's see where we're at. So our current last is 3. And now our node, we're at 4. Okay, let's see what we're doing here. So for 4, we've already done its left-hand side. So now we're here, if last, which we do have a last. So we are setting last dot right to be the current node, which is 4, and the current to be the current node, which is 3. So from here, then we go into the helper, the node dot right, which 4 does have a right, and it's 5. So, before we did that, we forgot to set last equal to node. So we have to make that update. So last is now equal to 4, and we are now moving on to the right. So now our node is 5, and this is the last node that we have left. So now, what are we doing? Same thing that we've been doing. So we say that last dot right is current node dot left. Oops, did that the wrong way. Current node dot left is last. And there is no right here. We set last equal, I'm doing that out of order again. We set last equal to the current node. So now last is equal to 5. There is no right. So we are done. Okay, we are done. So now we jump out of the helper function, and now what's left to do is to close the doubly linked list. Because notice here in our list, we go from 1 to 2 to 3 to 4 to 5, but we still need to make that circular closure happen. So how do we do that? Well, look here, we have these variables stored. We know that first equals 1 and last equals 5. So all I do is just repeat that same logic that I was doing in my recursion, where I was linking the last dot right, and now I'm saying last dot right equals first, and first dot left equals last. And now I'm done. So now what do I actually return to make this function call in place? Well, whenever you are working with binary trees or linked lists, you're always returning the head, because once you have the head, or the root of that object, you call next, you call left, you call right, you traverse it in that way. So what I'm going to just do is return that first element, which in this case is literally just called first. And with that, you have the implementation. Thanks so much for joining. See you again next time.